All right, welcome to this video, part of Unit 2 on Systems of Equations in Algebra 2. We're going to start, our first lesson of the unit is going to be a review of what you need to know from Algebra 1 on solving equations. And so we're going to do that now. We're going to review the different types of solutions to a linear system. So you can see if you have parallel lines, of course, there is no solution because the lines do not intersect. The solution is actually the point where the lines cross. So that is no solution. Now, we're going to add some terminology to this now, though, but we call a system like that inconsistent when there is no intersection. When there is an intersection, we call that system consistent. And it depends on whether there's going to be one solution, which would be consistent, and independent, meaning the two lines are not the same. One of them does not depend on the other. So that's when you get one solution, one set of coordinate points. And consistent dependent is when the two lines are the same line and they cross everywhere. They're dependent on each other for every single point. That's infinite solutions. As you learned in Algebra 1 and used in algebra or in geometry last year, there are three ways to solve a linear system. You can use algebraic techniques for which you can have substitution or elimination, and then graphing techniques where you just graph the two lines to see where they cross. So substitution can include transitive, like if both the equations equal y, they equal each other, or taking one equation and substituting it into the other one. Elimination is, of course, when you add the equations and you try to make something cancel out so that you can finish solving. So we're going to do an example with substitution, an example with elimination, and an example of graphing right now. So here's our first two examples. Put a line between them to give us some space to work. All right, so the first example has both lines in standard form, or general form as it's often called. When they're like that, usually you're going to want to use elimination. And on these, if I physically add them together right now, nothing cancels out. So I'm going to force something to cancel out. I'm going to go with the x's canceling. I'll multiply the top equation by 3 and the bottom equation by 4 so that I can turn this into a 12x and this into a negative 12x, and they will cancel. Now I need to finish distributing. 72. 120. Okay, so now my x's cancel when I add the equations together. I get 29y equals, of course, 120 plus 72 would be 192. All right. If I divide both sides by 29, all right, 29 does not go into 192 evenly, nor if I simplify the fraction does it reduce. So y is exactly 192 over 29, or approximately 6.62. So when you get a variable isolated and you get a value for it, if it's not a nice value that's easy to plug in, you're welcome to go back and eliminate again, but this time eliminate the other variable. 4x plus 3y equals 24. Negative 3x plus 5y. So there's my original two equations from up here. This time I'm going to eliminate the y's. I'm going to multiply the top equation by negative 5 and the bottom equation by positive 3 so that I will get a negative 15y and a positive 15y that add up to 0. Now I have to finish distributing. Okay, so my y's cancel. I have negative 29x equals negative 30. So x is 30 over 29, which is approximately 1.03. Okay, so I have my solution for this one. I have 30 over 29 for x, 192 over 29 for y, or 1.03, 6.62 approximately. So there's an example with elimination method. Now let's do an example with substitution method. That's where you look for, and when you have a variable already isolated, you can circle what it equals and plug it in for that variable in the other equation so that you can solve. So now I'm going to do negative 8x plus 2, and instead of y, I'm going to put 4x plus 12. So negative 8x plus 8x plus 24 equals 20. Okay, so on this one, something interesting is going to happen because the x's are going to cancel, and I'm going to end up with 24 equals 20, which is not true, which means this system has no solutions. We would call it inconsistent with our new terminology at the top of the notes because they are parallel lines. Just depending on your answer choices or how they ask you to answer it. If they ask you, what kind of lines are they? How many times do they intersect? There's no solutions. What type of system is it? Inconsistent. And you could describe it further by saying that they are parallel lines. So there's some algebraic techniques. On the next page of this, they are asking us to actually solve these by graphing. So we're going to do that. The first system, 4x plus 3y equals 24. And negative 3x plus 5y equals 30. Both of these are in standard form, so I'm going to graph them by doing x and y intercepts. So like for this line, if I put in 0 for the x, I get 30 divided by 5. That means that the y-intercept is 6. So the 0.06, I put in 0 for x by covering it up, and then I divide it. That is the y-intercept. Now I'm going to put in 0 for the y and get that the x-intercept is negative 10. Now, if for one reason one of your intercepts is not a nice intercept, you can always use the slope to graph the line. And the slope of a line in standard form is the opposite of a, so it would be 3 over the b, 5. All right, negative 10, 0. So now I have the 2 points. I also have my slope, 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3 over 5, up 3 over 5. And then that's all of that I can graph. So let's graph that line. Okay, now let's graph the other line. When you graph the first line, you want to fill up the grid. The second line, you just need to graph enough to see that it crosses the first one. Okay, my y-intercept, 0 for x, and then I solve, because 0 is going in for the x, I'm going to solve this and get 8. 0 for the y, and I'm going to solve this and get 6. 0, 8, 6, 0. My slope is down 4 over 3. So I could keep doing that to get more points, but I don't need to. I can already see where the lines cross. And it's not going to be at a perfect grid crosshairs because of the fact that, we already solved this and we got decimals. Our previous solution was about 1.03, about 6.62. And we can see just a little more than 1 and a little bit more than 6.5. That does confirm that answer that we got earlier. So this is 30 over 29, 192 over 29, which is approximately 1.03, 6.62. And you can also confirm that on Desmos as well to make sure that it's the correct answer, which I already did. So we don't need to do it again. I'm trying to write this more neatly. Maybe I'll highlight that just so we know that's the intersection point that we are looking for. Okay, so now for the other system, we have y equals 4x plus 12. Okay. We're not going to be able to graph the y-intercept on that easily, at least. And then negative 8x plus 2y equals 20. Okay. All right, I'm going to try and simulate the y-intercept because it isn't too far off the graph. Here's 11, here's 12, my y-intercept. And my slope is 4 over 1. So I can go backwards, down, 2, 3, 4, left 1. I don't know where the other one's going to cross it. So that's my line there that I'm going to plot. Okay. So that's the pink line. Now let's do the green one. This one's in standard form. The y-intercept, if I put in 0 for the x right here and solve, I get 10. So I put in 0 for the x, graph the y, and get 10. So here's the y-intercept. My slope is the opposite of the a number over the b number, which is also 4. So 1, 2, 3, 4 over 1. So we can see these two lines are running parallel to each other. Very, very, very closely, though. So I can graph them just like this, running parallel. So we can see there is no solution because they don't ever intersect. They're parallel lines. All right, so now we have a typical word problem or application scenario involving parallel lines. Systems of equations are used by businesses to determine a break-even point. This point describes where income and cost are equal. So that means after that, it helps you determine the point at which you stop incurring loss and start making a profit. So we're going to do this problem in which one of the equations is going to be what they spend and the other equation is going to be what they earn. So we have this business. The author wants the rights to publish her book. If one book costs $12 to produce and they plan to sell them for $24 each. So the revenue or income equation is y equals 24x, and x is the number of books. And y is the total money earned from those books or spent to buy the books. The cost equation, well, they pay $96,000 to the author for the rights, and each book costs them $12 to produce. So to produce the books, they're spending $12 for each book, plus the $96,000 that they gave to the author to get the rights to the book. So to find the point at which they would break even, we will use substitution method because they're both equal to y, or transitive, they're equal to each other. Okay, so I'm going to subtract 12x on each side. I get 12x equals 96,000. Now I'm going to divide both sides by 12. So 96,000 divided by 12 is 8,000. Oops. So they break even by selling 8,000 books. This means anything more than 8,000 books, they'll start making a profit. Anything less than 8,000 books, they're going to be at a loss as a business. Let's just take a look at this on Desmos because numbers this big, I wouldn't really expect you to graph them by hand, even though you could make a scale and do it. I've already graphed it though. Oh, by the way, these are our two previous ones. But I didn't want to look at that. I wanted to look at this one. Okay, so you can see right here, we have 8,192,000 8,000. So at 8,000 books, 192,000 is what they've spent or what they've made, their break-even point. You can play with, on Desmos, of course, you can play with your X and Y axis and make it so you can see things, which I've already pre-done that. And you can see this is the equation in red for what they spend. And this is the equation in blue for what they earn. So anything less than that 8,000 books, you can see the earning is less than what they're spending, so they're at a loss. Anything more than the 8,000 books, the earning equation is higher than the spending equation. So you can see that's where they're making a profit. I'm going to do a second video on this other half of this lesson where I review all the things about linear equations we should know from the past. So if you need to go over any of that, watch the second video when it comes out. And then after that, we will proceed to starting new stuff involving solving systems in Algebra 2.